Look up at the night sky tonight, and you're not just seeing stars, you're staring into a sea of galaxies, each one a swirling metropolis of billions of suns, planets, and mysteries we've only begun to unravel. What if I told you that some of these galaxies are so far away their light has traveled for billions of years just to reach your eyes, that you're literally looking into the past every time you gaze upward? The universe is far stranger, more violent, and more beautiful than we could ever imagine. And today, we're going on a journey to the edges of cosmic understanding. Think about this for a moment. Our Milky Way is just one of an estimated 2 trillion galaxies in the observable universe, and yet we've barely scratched the surface of what's out there. Some galaxies are cannibals, devouring their neighbors in slow-motion collisions. Others hide supermassive black holes so powerful they warp space itself. Then there's the eerie enigma of dark matter, an invisible force binding galaxies together, making up most of the universe's mass, yet remaining utterly invisible to us. How is any of this possible, and what does it mean for our place in the cosmos? That's exactly what we're exploring today. Over the next 25 mind-bending facts, you'll discover galaxies that defy logic, cosmic phenomena that challenge everything we thought we knew, and revelations that will leave you questioning the very fabric of reality. This isn't just a tour of distant stars, it's a journey into the unknown where the rules of physics twist into strange new shapes and the universe reveals its deepest secrets. So buckle up. By the time we're done, the night sky will never look the same to you again. Here's something that will twist your perception of the universe. Every galaxy you see is racing away from us at unimaginable speeds, not because they're moving through space, but because space itself is stretching. Picture a loaf of raisin bread baking in the oven. As the dough expands, every raisin moves farther apart, not because they're traveling through the dough, but because the dough itself is growing. That's exactly what's happening to our cosmos. Edwin Hubble first noticed this in the 1920s when he realized distant galaxies weren't just drifting, they were fleeing faster the farther away they were. This discovery shattered the old idea of a static universe and revealed something far stranger. Space is stretching, carrying galaxies along like leaves on a rushing river. Some of these galaxies are moving so fast, their light can barely reach us before space stretches it into oblivion. The most distant ones are receding at nearly the speed of light, their light stretched into faint, invisible whispers by the time it crosses the cosmic void. This isn't just a curiosity, it has terrifying implications. If this expansion keeps accelerating, as many scientists believe, one day galaxies beyond our local group will vanish from view entirely, their light stretched beyond detection. Future astronomers might look up at a sky nearly empty of galaxies, never knowing the universe was once teeming with them. But here's the real kicker: this expansion isn't just happening out there. It's happening everywhere, all at once. The space between atoms in your body is technically expanding too, just on such a tiny scale that gravity and other forces hold everything together. The universe is stretching like an infinite rubber sheet, and we're all along for the ride. What's driving this? A mysterious force called dark energy, making up nearly 70% of the cosmos, yet we still don't fully understand it. One thing's certain: the universe isn't just expanding, it's accelerating, racing toward a future we can barely imagine. Our galaxy isn't just drifting peacefully through space, it's headed straight for a cosmic wrecking ball. 4.5 billion years from now, the Milky Way will slam into the Andromeda galaxy in one of the most spectacular collisions the universe has ever witnessed. Right now, Andromeda is hurtling toward us at 250,000 miles per hour, pulled in by the irresistible grip of gravity. When these two titans finally meet, it won't be a violent crash of stars exploding in fireballs, but something far more mesmerizing, a slow, graceful dance of destruction and rebirth. Picture this: as the galaxies draw closer, their spiral arms will begin to stretch and warp, twisting into long, luminous ribbons of stars and gas. Gravity will fling entire star systems into new orbits, sending some hurtling toward the galactic center while others are tossed into the void. Over billions of years, the two galaxies will pass through each other multiple times, each encounter reshaping them further until they finally settle into a single, massive elliptical galaxy. Astronomers call this future hybrid Milky, a cosmic monument to the universe's relentless transformation. Here's the wildest part: despite the sheer scale of this collision, the chances of stars actually hitting each other are almost zero. Space is so vast that even in a galaxy of hundreds of billions of stars, the distances between them are unimaginably huge, but don't mistake that for safety. The gravitational turbulence will be catastrophic, ripping planets from their orbits and flinging some into the freezing darkness of intergalactic space. Any civilizations alive by then would witness the night sky unraveling, as familiar constellations vanish and new ones emerge in a dazzling, ever-shifting display. Andromeda isn't just our galaxy's future, it's a mirror of our past. Most large galaxies, including ours, were built through mergers like this, growing by swallowing smaller neighbors. In fact, we've already absorbed dozens of dwarf galaxies, and one day, even the Milky Way's twin will become part of something greater. This is the universe's grand cycle. Galaxies collide, stars are born from the chaos, and the cosmic dance continues. We might not be around to see it, but the legacy of this collision will echo for trillions of years. While we often picture galaxies as vibrant, star-forming powerhouses, some have reached a cosmic dead end, frozen in time with no new stars being born. These are the red and dead galaxies, celestial graveyards where the lights are slowly going out. Their nickname comes from their eerie crimson glow, a telltale sign of aging stars that have burned through their fuel, leaving behind cooler, redder embers. Unlike spiral galaxies like our Milky Way, bustling with stellar nurseries, these galaxies are barren, their gas reserves drained or stolen long ago. What could possibly kill an entire galaxy? The culprits are as dramatic as they are destructive. In dense galaxy clusters, where hundreds of galaxies huddle close together, gravitational tug-of-wars can rip away their precious star-forming gas. Imagine a galactic mugging on a cosmic scale. Smaller galaxies passing too close to a massive neighbor might have their gas stripped away, leaving them starved and lifeless. But there's another suspect lurking at the heart of these dead galaxies: supermassive black holes. When these monsters feed, they unleash torrents of energy so powerful they can heat up or blast away a galaxy's gas reserves, effectively shutting down star formation. It's like a cosmic furnace burning through the very fuel needed to keep the galaxy alive. The most haunting part: this could be the fate awaiting most galaxies. As the universe ages and galaxy clusters grow denser, more and more galaxies may fall victim to these processes, turning from vibrant blue spirals into silent red relics. But even in death, these galaxies tell a story. By studying them, astronomers piece together the life cycle of galaxies: how they're born, how they thrive, and what ultimately brings about their end. It's a reminder that even the mightiest structures in the universe aren't eternal. They evolve, they fade, and sometimes they simply run out of time. Yet there's a strange beauty in these galactic ghosts. Their red glow is the light of countless ancient stars, some nearly as old as the universe itself, shining faintly like embers in the cosmic dark. They may no longer create new stars, but they're not entirely lifeless. Their surviving stars will continue burning for billions of years, a quiet testament to the galaxy's former glory. And who knows, in the distant future, perhaps even our Milky Way will join their ranks, its spiral arms fading as the last of its gas is spent, leaving behind only the dim, red glow of aging stars. The universe has a way of recycling everything, even galaxies. Galaxies aren't just what we see, they're cloaked in shadows, their true forms hidden in plain sight. What if I told you the stars, gas, and dust we observe in a galaxy are just the tip of the cosmic iceberg? Up to 90% of a galaxy's mass is invisible, made of something so mysterious it defies detection: dark matter. This ghostly substance doesn't glow, reflect, or interact with light in any way. It doesn't collide with atoms or gather into planets, yet without it, galaxies as we know them wouldn't exist at all. Take a spiral galaxy like the Milky Way. Its stars orbit the center at speeds so fast, the galaxy should have torn itself apart billions of years ago. The gravity from visible matter alone isn't nearly strong enough to hold everything together. So what's keeping these stars from flinging into the void? An invisible scaffold of dark matter, woven through and around the galaxy like an enormous, unseen hand gripping the stars in place. We can't see it, but we know it's there because without its gravitational pull, galaxies would unravel like spinning tops, losing their balance. The hunt for dark matter reads like a cosmic detective story. Astronomers first noticed its effects in the 1930s when studying the Coma Cluster, a massive group of galaxies. The galaxies moved so fast that the cluster's visible mass couldn't possibly hold them together. Something unseen had to be providing the extra gravity. Decades later, Vera Rubin's groundbreaking work on galaxy rotation curves confirmed it. Stars at the edges of spiral galaxies orbit just as fast as those near the center, defying the laws of gravity as we understood them. The only explanation, a massive halo of dark matter enveloping each galaxy, its gravity shaping the motion of everything within. Here's where it gets even stranger. Dark matter isn't just a passive backdrop, it's the architect of the universe's large-scale structure. After the Big Bang, dark matter's gravity acted like a cosmic scaffold, pulling ordinary matter into the filaments and voids we see in today's galaxy maps. Without it, galaxies might never have formed at all. Yet despite its overwhelming influence, we still don't know what dark matter actually is. Is it a particle, a shadow universe of matter we can't perceive, or something even more bizarre that rewrites the rules of physics? Experiments deep underground in space and at particle colliders worldwide are searching for answers, but dark matter remains elusive. It's the universe's ultimate ghost, felt but never seen, and that's what makes it so thrilling. Solving this mystery wouldn't just explain galaxies, it could unveil entirely new laws of nature. Until then, every galaxy we observe is a reminder. The cosmos is far stranger than it appears, hiding its greatest secrets in the darkness between the stars. The universe wasn't always filled with galaxies. There was a time when the cosmos was a dark, empty void, still reeling from the chaos of the Big Bang. So when astronomers spotted GNZ 11, a galaxy so ancient its light began traveling toward us just 300 million years after the universe's birth, it was like finding a toddler's footprint in primordial mud. This galaxy is the oldest we've ever seen, a flickering candle in the cosmic dark, and its very existence pushes the boundaries of what we thought possible in the early universe. GNZ 11 isn't just old, it's baffling. Nestled in the constellation Ursa Major, this galaxy blazes with the light of newborn stars, shining brighter than many younger galaxies despite its age. When Hubble first captured its faint glow, astronomers were stunned. How could a galaxy this luminous form so soon after the Big Bang? The early universe was supposed to be a turbulent, gas-choked mess, yet GNZ11 defies expectations, churning out stars 20 times faster than our Milky Way does today. It's as if we stumbled upon a bustling city in what we thought was an uninhabited wilderness. Here's what makes this discovery so revolutionary. GNZ11's light has been stretched by the expansion of space into the infrared, a wavelength invisible to our eyes. By the time this ancient starlight reached Hubble's lenses, it had traveled 13.4 billion years, nearly the entire age of the cosmos. We're not just looking at a distant object, we're peering back into a time when the universe was less than 2% of its current age. The photons hitting Hubble's sensors began their journey before Earth, the Sun, or even the Milky Way existed. But GNZ11 isn't just a relic, it's a Rosetta Stone for cosmic history. Its rapid star formation suggests the early universe was far more dynamic than we imagined, with pockets of gas collapsing into galaxies much sooner than models predicted. Some theories even suggest these ancient galaxies might have been powered by supermassive black holes, their ferocious energy igniting star birth like a match tossed into dry tinder. Others propose they formed in rare, dense regions where gravity worked overtime, sculpting galaxies ahead of schedule. The James Webb Space Telescope has since turned its infrared eyes toward GNZ11 and its peers, peeling back even more layers of the universe's infancy. With every observation, we're rewriting the story of how galaxies, and by extension we, came to be. GNZ11 is more than a record holder. It's a beacon from the dawn of time, challenging us to rethink how quickly the cosmos woke up, how stars first ignited, and what secrets still lurk in the darkness of the early universe. One thing's certain, the deeper we look, the more we realize how little we truly know. Galaxies missing their dark matter sound like something out of a cosmic horror story, like a house standing without its foundation or a tree floating without roots. Yet NGC 1052DF2 is real, a ghostly galaxy drifting through space with almost no trace of the invisible glue that holds most galaxies together. This isn't just unusual, it's revolutionary. For decades, dark matter was considered the backbone of galaxy formation, the hidden hand shaping everything from spirals to ellipticals. But this strange object and others like it flipped the script entirely, forcing astronomers to confront a baffling question. How does a galaxy even exist without the very thing we thought was essential? The mystery starts with motion. In most galaxies, stars on the outskirts orbit at speeds that should send them flying into the void unless an unseen mass, dark matter, is anchoring them in place. But when researchers measured the movement of star clusters in NGC 1052DF2, the math didn't just hint at missing dark matter, it screamed it. The stars were moving sluggishly, as if nothing invisible was tugging on them at all. It's like watching a car race where one vehicle glides effortlessly while the others struggle uphill, except in this case, the missing hill is an entire cosmic ingredient. So where did its dark matter go? One leading theory is as dramatic as it sounds: galactic robbery. Picture two galaxies colliding, their dark matter halos tangling like spiderwebs in the wind. In the chaos, a smaller galaxy could be stripped bare, its dark matter ripped away by gravitational forces while its stars, more densely packed, remain behind. Another possibility is that these oddballs formed differently from the start, perhaps in rare pockets of the early universe where gas collapsed into stars without the usual dark matter scaffolding. Either way, their existence cracks open a door to alternative galaxy building recipes we never knew existed. The implications ripple far beyond one peculiar galaxy. If dark matter isn't always mandatory, our models of cosmic evolution need rewiring. Maybe some galaxies bootstrap themselves through sheer star power, their stellar winds and supernova clearing out dark matter like a cosmic broom. Or perhaps dark matter isn't as uniform as we thought, with deserts scattered throughout the universe where it's strangely absent. Every new discovery in this category, like DF4, another dark matter-deficient ghost, adds another puzzle piece, challenging us to rethink how galaxies live, die, and defy expectations. What's most thrilling is how these outliers prove the universe still has tricks up its sleeve. For every rule we think we've nailed down, there's a celestial rebel breaking it. NGC 1052DF2 isn't just a curiosity, it's a cosmic provocateur, daring us to question what we're sure we know. And in that challenge lies the heart of science, not just confirming theories, but discovering the exceptions that push our understanding further into the unknown. We think of galaxies as vast, but IC 1101 redefines the word completely. A cosmic colossus stretching 4 million light-years from end to end. To put that into perspective, if our Milky Way were the size of a basketball, this galaxy would dwarf an entire football field. Its sheer scale isn't just impressive, it forces us to ask how nature builds something so enormous and whether there's a limit to how big a galaxy can grow. Most supergiant galaxies like IC 1101 aren't loners, they're the bullies at the center of crowded galaxy clusters, where gravity feeds them a steady diet of smaller neighbors. Picture a cosmic spider sitting at the heart of its web, pulling in passing galaxies over billions of years. Each merger adds stars, gas, and dark matter to the growing behemoth, stretching it further into the void. But IC 1101 didn't just grow by chance. It's the product of a perfect storm, a privileged position in a dense cluster, relentless mergers, and a supermassive black hole at its core that may have fueled its expansion. Here's where it gets even wilder. The stars on the outer edges of this galaxy move so slowly that a single orbit could take 1 trillion years longer than the current age of the universe. That means many of these stars will never complete a full trip around their galactic home. Yet despite its size, IC 1101 isn't bustling with star formation. Like an overgrown city that's exhausted its resources, it's mostly filled with ancient red stars, their faint glow a testament to a frenzied youth that's long since passed. What's truly humbling is realizing this might not even be the upper limit. Theoretical models suggest galaxies could grow even larger under the right conditions, perhaps reaching 10 million light-years across if they dominate their clusters for long enough. But there's a catch: the accelerating expansion of the universe might eventually tear these titans apart, stretching their outer stars into isolation before they can grow further. IC 1101 isn't just a record holder, it's a window into the extremes of cosmic evolution. It shows us how gravity, time, and sheer persistence can sculpt structures so vast they defy intuition. And somewhere out there, even larger galaxies might be lurking, waiting for our telescopes to reveal them, reminding us that the universe always has a way of surpassing our wildest expectations. Imagine a star moving so fast it doesn't just zip through its galaxy, it breaks free entirely, hurled into the void with enough speed to escape gravity's grasp forever. These are hypervelocity stars, cosmic fugitives racing through space at millions of miles per hour, their origins tied to some of the most violent events in the universe. While most stars orbit their galaxies like commuters on a circular route, these outliers are more like bullets fired into the darkness, never looking back. The story of how stars reach such extreme speeds reads like a cosmic thriller. The most likely culprit, a supermassive black hole lurking at the galaxy's heart. Picture a binary star system, two stars locked in a mutual orbit, wandering too close to the black hole's gravitational grip. In a gravitational slingshot maneuver, one star gets captured, while the other is flung outward with such force it reaches escape velocity. It's like a cosmic game of crack the whip, where the black hole's immense gravity provides the final, devastating tug. These ejected stars don't just drift away, they rocket outward at speeds exceeding 1 million miles per hour, fast enough to cross the distance between Earth and the Moon in under 15 minutes. But black holes aren't the only architects of these stellar speedsters. Galactic collisions can also send stars careening into the void. When two galaxies merge, their gravitational interactions can fling stars like pinballs, some accelerated so fiercely they break free entirely. Others might be propelled by supernova explosions, their violent births kicking them out of their home systems with a force no gravity well can contain. No matter the cause, the result is the same: stars stripped from their galactic homes, doomed to wander the emptiness between galaxies, where the nearest neighbor might be millions of light years away. Tracking these rogue stars is like following breadcrumbs back to the scene of a cosmic crime. Their trajectories reveal secrets about the environments that ejected them, whether it was a black hole's ruthless gravity or the chaos of a galactic pile-up. Some hypervelocity stars even carry chemical signatures hinting at their origins, like cosmic fingerprints left behind. One of the most famous, known as S5HV-S1, is racing through the Milky Way's outskirts at over 1.7 million miles per hour, a speed so staggering it will eventually leave our galaxy behind entirely. What's haunting is the fate awaiting these stellar exiles. With no galaxy to call home, they'll drift through the freezing void, their light growing ever dimmer. Planets orbiting them, if any survived the ejection, would face an eternal night, their skies devoid of neighboring stars. Yet even in their isolation, these stars serve a purpose. By studying them, astronomers piece together the violent histories of galaxies, uncovering the hidden forces that shape the cosmos. Every hypervelocity star is a messenger, telling a story of gravitational mayhem, cosmic collisions, and the incredible energies lurking at the hearts of galaxies. And here's the twist: our own sun, though comfortably orbiting the Milky Way now, could one day share a similar fate. If another star passes too close, or if the galaxy's central black hole gets a gravitational grip on the wrong system, even familiar stars could be sent hurtling into the abyss. It's a reminder that in the grand scheme of things, no star is truly safe. The universe is a place of chaos and wonder, where even the most stable-seeming objects can become cosmic projectiles in the blink of an eye. Wrap your mind around this. If you scooped up every grain of sand on every beach, every desert dune, and every ocean floor across our entire planet, you'd still fall short of the number of galaxies swirling through the observable universe. Current estimates place the count at over 2 trillion, each one a colossal gathering of stars, planets, and untold cosmic phenomena. To grasp how incomprehensibly vast that number is, imagine setting off on a journey to explore them all. Even if you could visit a new galaxy every single second without pause, it would take you trillions of years just to glimpse them. That's longer than the current age of the universe itself. This revelation comes from deep-field images captured by telescopes like Hubble, which pointed at seemingly empty patches of sky for days, revealing thousands of faint smudges, each one a distant galaxy. Extrapolating those observations across the entire cosmos, astronomers arrived at this staggering figure. But here's what's even more astonishing: 2 trillion is likely an undercount. With every technological leap, from the James Webb Space Telescope to future observatories, we're peeling back deeper layers of the universe, finding galaxies hiding in the shadows, their light too dim or stretched for previous instruments to detect. Some estimates suggest the true number could be 10 times higher once we account for these cosmic ghosts. Consider what this means for the scale of existence. Within each of those galaxies, there are hundreds of billions of stars, many with planets orbiting them. The math becomes dizzying, more worlds than all the seconds that have ticked by since the Big Bang. It's a numbers game so vast it renders human intuition useless. And yet, despite this unimaginable abundance, we've only mapped a fraction of a percent of what's out there. Our Milky Way's nearest neighbor, Andromeda, feels impossibly distant at 2.5 million light-years away. But on the grand cosmic ledger, it's practically our next-door neighbor. This cosmic census also carries a humbling reminder. Everything we see, even with our most powerful tools, is just the observable universe, the portion of the cosmos whose light has had time to reach us in 13.8 billion years. Beyond that horizon, space is expanding so fast that light from those regions will never reach Earth. There could be infinitely more galaxies forever hidden from view, their existence left to the realm of theory. The 2 trillion we know might just be the opening chapter of a story with no conceivable end. What's truly exhilarating is how this changes our understanding of possibility. With so many galaxies, the odds tilt dramatically toward the existence of other life, other civilizations, and other wonders we can't yet fathom. It's like standing on the shore of an ocean so vast you can't see the other side, knowing each wave carries secrets waiting to be uncovered. The universe isn't just big, it's a tapestry of infinite variety, with each thread representing a galaxy whose story we've only begun to read. And somewhere in that unimaginable expanse, our tiny pale blue dot orbits an ordinary star in an ordinary galaxy, reminding us that the greatest cosmic miracles might still lie ahead. When we picture galaxies, spirals like the Milky Way or smooth ellipticals usually come to mind, but the universe has a flair for the unconventional. Meet the Tadpole Galaxy, a cosmic oddball with a tail stretching 280,000 light-years behind it, as if some celestial painter flicked their brush across the void. This bizarre shape isn't artistic license, it's the aftermath of a gravitational mugging. Sometime in the distant past, a smaller galaxy strayed too close, and the tadpole's spiral arm was yanked outward like taffy, leaving a trail of stars and gas in its wake. What's astonishing is that this tail isn't just debris, it's a stellar nursery with newborn stars glowing blue against the darkness, proving even chaos can spark creation. Then there's Hoag's object, a galaxy so perfectly ring-shaped it looks like a cosmic bullseye. At its center, a dense cluster of ancient yellow stars glows softly, surrounded by a luminous blue ring of young, hot stars with near-empty space in between. How does such a structure form? One theory suggests a smaller galaxy punched through Hoag's center billions of years ago, sending shockwaves rippling outward that triggered star formation in a precise circle. Another proposes it's the result of unstable internal dynamics, like a spinning water droplet separating into rings. Whatever the cause, Hoag's object defies every textbook model, a reminder that galaxies don't always follow the rules. But perhaps no galaxy wears its history more dramatically than the Cartwheel. Picture a stone tossed into a pond. Now imagine that pond is a spiral galaxy, and the stone is another galaxy barreling through its center at 500,000 miles per hour. The collision sent shockwaves cascading through the Cartwheel's gas clouds, compressing them into a brilliant ring of star formation that expanded outward like ripples. Today, it's a snapshot of cosmic violence frozen in time, with its central region still reeling from the impact while the outer ring blazes with newborn stars. What's eerie is that the intruder galaxy escaped nearly unscathed, a ghostly witness to the chaos it left behind. These misfit galaxies aren't just curiosities, they're time capsules of extreme events. The Medusa merger, for example, shows two galaxies so thoroughly entwined that their identities have blurred into a tangle of star streams resembling celestial serpents. Meanwhile, the antennae galaxies are locked in a slow-motion collision, their long tidal tails bristling with star clusters flung into space like sparks from a grindstone. Each of these shapes tells a story of gravitational encounters, cosmic accidents, and the universe's relentless creativity. What's humbling is realizing these oddities might be more common than we thought. Up to 5% of all galaxies could be ring-shaped, while others sport warped disks, polar rings, or even X-shaped cores. With every new telescope, we uncover more of these rule breakers, each one challenging our assumptions about how galaxies evolve. They prove the cosmos isn't just a gallery of pristine spirals and ellipticals. It's a workshop where gravity bends, twists, and sculpts matter into forms as wild as the forces that shape them. And somewhere out there, another strange galaxy is waiting to be found, ready to rewrite the rules all over again. At the heart of nearly every galaxy, hidden in the swirling chaos of stars and gas, lies a monster, a supermassive black hole so dense it warps space and time around it. These aren't just any black holes, they're cosmic titans, weighing in at millions or even billions of times the mass of our Sun. The Milky Way's own Sagittarius, a star, is a perfect example. A silent giant lurking 26,000 light-years away, its gravity holding our galaxy together like an invisible anchor. But don't let its quiet demeanor fool you. When these beasts wake up, they unleash energies so fierce they can outshine entire galaxies. How does something so destructive end up at the center of almost every large galaxy? The answer lies in the universe's earliest days. When the first galaxies formed, their cores were dense cauldrons of gas and stars, collapsing under their own weight. Over time, these collapsing cores birthed black holes that grew by devouring everything around them: gas, dust, even other stars. Some became so massive their gravity dictated the fate of their entire galaxy. It's a cosmic balancing act. The black hole feeds, but its explosive energy can also blow away the very material it needs to grow, putting a cap on its size. The most extreme versions of these monsters are quasars, black holes so voracious they light up the early universe. Picture a disk of superheated gas spiraling into oblivion, glowing brighter than 1 trillion suns as it's torn apart by gravity. These are the brightest objects in existence, visible across billions of light-years, their light fossilized from a time when galaxies were young and chaos ruled. Today, most quasars have gone quiet as their fuel ran out, but their legacy remains etched into the cosmos. Yet black holes aren't just destroyers, they're architects. Their powerful jets, spewing particles at near light speed, can heat up surrounding gas so intensely it shuts down star formation across entire galaxies. This is why some galaxies die young, their stellar nurseries snuffed out by the very engine at their core. But paradoxically, these jets can also trigger star birth in distant gas clouds, compressing them just enough to ignite new suns. It's a delicate dance of creation and destruction, with the black hole playing both roles. What's truly mind-bending is the scale of their influence. The supermassive black hole in galaxy M87, famously photographed in 2019, weighs 6.5 billion solar masses, a gravitational titan whose shadow stretches wider than our entire solar system. And then there's TON 618, a quasar so massive it defies current physics, its black hole clocking in at 66 billion solar masses. How something this colossal formed so quickly after the Big Bang remains one of astronomy's greatest puzzles. These black holes are more than just galactic curiosities. They're proof that the universe thrives on extremes. From silent giants like Sagittarius, a star, to the dazzling quasars of the ancient cosmos, they shape the destiny of galaxies in ways we're only beginning to understand. And as we peer deeper into the abyss, one thing becomes clear. The heart of every galaxy holds a secret, a darkness so profound it bends the rules of reality itself. In the vast cosmic menagerie of galaxies, the so-called green peas stand out as tiny but mighty powerhouses, defying expectations with their explosive stellar fireworks. These peculiar galaxies, no larger than a tenth of the Milky Way size, earned their whimsical nickname from astronomers who first spotted them in citizen science projects, their small, round shapes and vivid green hues standing out like scattered peas against the darkness of space. But don't let their unassuming appearance fool you. What they lack in size, they make up for in sheer ferocity, birthing stars at rates that dwarf our own galaxy's modest output. The secret to their emerald glow lies in oxygen. Unlike the calm, balanced spirals we're familiar with, green pea galaxies are crammed with ionized oxygen gas, energized by the relentless barrage of ultraviolet light from newborn stars. This oxygen emits a specific shade of green when excited, giving these galaxies their distinctive color. It's like comparing a tranquil lake to a churning geyser. Both contain water, but one is boiling over with activity. In the case of green peas, that activity is star formation on a scale so intense it reshapes our understanding of how galaxies evolve. What's truly staggering is the pace at which they work. While the Milky Way quietly produces 1 or 2 new stars per year, a single green pea galaxy can forge hundreds, even thousands, in the same span. Imagine a small town suddenly outproducing a megacity in sheer industrial output. That's the level of cosmic overachievement we're dealing with. This frenzy isn't just impressive, it's a throwback to the universe's earliest epochs when galaxies were smaller, gas was more abundant, and star birth happened in violent, unchecked bursts. In many ways, green peas are living fossils, offering us a glimpse into the conditions that dominated the cosmos billions of years ago. But how do they sustain such extreme rates of star formation? The answer lies in their pristine gas reserves. Unlike older galaxies, where heavy elements from dead stars pollute the interstellar medium, green peas are relatively unspoiled, their gas clouds remaining pure and fertile. Without the pollution of heavier elements, their gas cools more efficiently, collapsing into stars with reckless abandon. It's like comparing a wildfire in dry brush to a controlled burn. The former spreads uncontrollably, just as star formation runs wild in these unspoiled environments. Yet their brilliance is fleeting. Such ferocious star formation can't last forever. Eventually, these galaxies will either exhaust their gas reserves or, ironically, be quenched by the very stars they create. Supernova and stellar winds will blow away the remaining gas, leaving behind a quieter, aging galaxy. Some might merge with larger neighbors, their legacy absorbed into a greater whole. But for now, they blaze brightly, their green glow a testament to the universe's capacity for both violence and beauty on a scale we're only beginning to comprehend. The discovery of green pea galaxies underscores a profound truth. Size isn't everything in the cosmos. Even the smallest galaxies can host the most extraordinary phenomena, challenging our assumptions about where and how cosmic wonders arise. As telescopes like James Webb peer deeper into the early universe, they may reveal countless more of these celestial overachievers, each one a clue to the chaotic, star-filled dawn of galactic evolution. And in their vibrant glow, we find a reminder sometimes the universe's most fascinating stories come in the smallest packages. Galaxies might seem like peaceful islands of stars, but beneath their serene glow lies a history of cosmic violence. Some grow not by creating stars, but by devouring their neighbors. This process, known as galactic cannibalism, is the universe's ultimate survival of the fittest, where larger galaxies feast on smaller ones, growing more massive with every merger. Picture a celestial predator stalking its prey. Gravity pulls a smaller galaxy inexorably closer until tidal forces stretch it into long, luminous streams of stars like cosmic spaghetti. Over time, these remnants are absorbed completely, leaving behind only faint trails as evidence of the feast. Our own Milky Way is no stranger to this behavior. Wrapped around it like celestial graffiti are the ghostly remains of dwarf galaxies it has consumed over billions of years. One of the most famous, the Sagittarius dwarf spheroidal, is currently being torn apart, its stars scattered into a looping river of light around our galaxy's edges. Then there's Gaia Enceladus, a long-dead dwarf galaxy whose stars now mingle with the Milky Ways, their chemical fingerprints betraying their violent past. These mergers aren't just historical footnotes, they're how galaxies like ours grow, stealing stars and gas to fuel future generations of suns. Andromeda, our nearest galactic neighbor, takes cannibalism to another level. Its halo, a vast, diffuse cloud of stars surrounding its main disk, is littered with the debris of past meals. Some of these stellar streams are so massive they stretch hundreds of thousands of light years, tracing the orbits of galaxies consumed billions of years ago. One study even suggests Andromeda's halo contains the mangled remains of at least 2 large galaxies it devoured in the last few billion years. The evidence is written in the motions of stars, their paths twisted by gravitational encounters long after their parent galaxies were destroyed. But why does this happen? It all comes down to gravity's relentless pull. In dense galaxy clusters, smaller galaxies orbiting larger ones lose energy over time, spiraling inward until they're ripped apart. Sometimes the process is slow, stretching across billions of years. Other times, galaxies collide head-on, triggering explosive bursts of star formation as their gas clouds compress. The result is a galactic metamorphosis. Spiral galaxies merge into featureless ellipticals, their delicate structures erased by the chaos of collision. The eeriest part, this cannibalism isn't just a relic of the past, it's the future. The Milky Way and Andromeda are on a collision course, destined to merge into a single, larger galaxy astronomers call Milkomda. When that happens, the 2 spirals will shred each other's structures, their stars flung into new orbits, their gas compressed into new suns. The remnants of both galaxies will become indistinguishable, just as the dwarfs they once consumed are now part of them. It's a cycle as old as the universe itself. Galaxies grow by eating others, ensuring their survival in a cosmos where only the massive endure. Yet these mergers aren't just destructive, they're creative. The shockwaves from galactic collisions trigger star birth, lighting up the cosmos with new stellar nurseries. Even our solar system might owe its existence to a long-ago merger that stirred the Milky Way's gas into forming the Sun. Every time we look up at the night sky, we're seeing the aftermath of these ancient feasts, a testament to the universe's endless appetite for reinvention. The stars above aren't just points of light, they're the survivors of a cosmic food chain where galaxies rise by consuming, and the universe writes its history in stolen starlight. The universe's first galaxies weren't the majestic spirals or blazing ellipticals we see today. They were cosmic infants, small and fragile, flickering to life in the darkness of the early cosmos. Picture a campfire struggling to stay lit in a downpour. These primordial galaxies were just like that, their star-forming efforts sporadic and feeble, their light barely piercing the thick fog of hydrogen gas that filled the universe. Without the heavy elements we take for granted, carbon, oxygen, iron, their chemistry was starkly simple, relying solely on hydrogen and helium left over from the Big Bang. This lack of cosmic ingredients meant their stars burned hotter, died younger, and exploded with unmatched ferocity, seeding the universe with the first heavy elements that would later build planets and life. What's astonishing is how different these early galaxies were from modern ones. Without the stabilizing influence of heavier elements, their gas couldn't cool efficiently, leading to chaotic bursts of star formation followed by long, quiet periods. Imagine a car engine sputtering to life, roaring for a moment, then stalling. This was the rhythm of the cosmos in its infancy. These galaxies were also tiny by today's standards, some no larger than 1 million stars, a far cry from the hundreds of billions in galaxies like our Milky Way. Yet these modest beginnings held the blueprint for everything that followed. The James Webb Space Telescope is rewriting the story of these cosmic pioneers. With its infrared eyes, Webb pierces the veil of time, capturing light from galaxies so ancient their stars ignited when the universe was just 2% of its current age. One of its earliest discoveries, Jade's GSE 13-0, is a prime example, a galaxy so small and faint it's barely more than a smudge in the data, yet it existed a mere 300 million years after the Big Bang. Its stars, though few in number, were likely massive and short-lived, their deaths scattering the first heavy elements into the void. But here's the twist: these early galaxies might have been more numerous than we ever imagined. Recent Webb observations suggest the early universe was peppered with faint, tiny galaxies, their collective light contributing to the cosmic dawn, the epoch when the first stars and galaxies burned away the hydrogen fog in a process called reionization. It's like discovering an entire hidden chapter in a book you thought you knew by heart. Each of these galaxies, though individually dim, played a role in transforming the universe from a dark, featureless expanse into the glittering cosmic web we see today. What's humbling is realizing how much we still don't know. Were these early galaxies the seeds of today's supermassive black holes? Did they merge quickly or drift alone for billions of years? Every new Webb image brings us closer to answers, but also raises fresh questions. One thing's certain: the universe started small, its first galaxies flickering like candles in the wind, but from those fragile flames came everything we see and everything we are. If you zoom out far enough, galaxies aren't scattered randomly. They're strung like beads on invisible threads, weaving a tapestry so vast it defies comprehension. This is the cosmic web, the universe's grand architecture, where galaxies cluster along sprawling filaments of dark matter, separated by voids so empty they feel like cosmic deserts. Picture a spider's web spun on a scale beyond human imagination, its strands stretching hundreds of millions of light years, with galaxies glittering at the intersections like dewdrops. This isn't just a pretty pattern, it's the fingerprint of the universe's birth, a relic of the tiny fluctuations in density that emerged from the Big Bang's chaos. The Webb's framework is built by dark matter, that mysterious, invisible substance making up most of the universe's mass. After the Big Bang, dark matter's gravity acted like a cosmic scaffold, pulling ordinary matter into its tangled filaments. Over billions of years, gas and dust followed these invisible roads, condensing into galaxies at the densest knots. The result, a universe organized into a vast network, where galaxies huddle along filaments like cities along highways, while the voids between them remain almost devoid of matter. Some of these voids are so staggeringly empty, They span hundreds of millions of light-years regions where, if you stood on a hypothetical planet, the night sky would be nearly black, with only a faint smudge or two hinting at the universe beyond. What's truly mind-bending is how perfectly this structure mirrors early universe simulations. Scientists can recreate the cosmic web's formation by modeling dark matter's gravitational pull, and the results match our observations with uncanny precision. It's as if the universe left behind a blueprint and we're only now learning to read it. The Sloan Digital Sky Survey, one of the most ambitious mapping projects in history, has revealed this web in stunning detail, charting millions of galaxies and exposing the delicate filaments connecting them. Each new survey peels back another layer, showing how galaxies align along these threads like compass needles pointing to hidden forces. But the cosmic web isn't just a static relic, it's a dynamic, evolving structure. Galaxies drift along filaments over cosmic time, drawn toward the intersections where multiple strands meet. These nodes, known as galaxy clusters, are the universe's metropolises, home to thousands of galaxies bound together in a gravitational frenzy. The largest, like the Coma cluster, are so massive they bend space itself, distorting the light from galaxies behind them into faint, ghostly arcs. Meanwhile, the voids keep expanding, their emptiness stretching as the universe grows, leaving isolated galaxies stranded like cosmic castaways. This grand design raises profound questions. Why do galaxies obey this intricate pattern? What determines which regions become dense filaments and which become voids? And could there be even larger structures we haven't detected yet? Some theories suggest the cosmic web might extend far beyond what we can observe, its true scale lost to the accelerating expansion of the universe. Others speculate that the web's structure could hold clues to dark energy, the mysterious force driving that expansion. Standing back, the cosmic web reminds us of the universe's paradoxical nature, both orderly and chaotic, vast yet intricately connected. It's a structure so enormous we can barely perceive it, yet its patterns echo the smallest ripples of the Big Bang. Every galaxy, from the brightest spiral to the faintest dwarf, is part of this web, a single thread in a tapestry woven by gravity, dark matter, and time. And as we map more of its strands, we're not just charting the universe, we're tracing our own place within it, one filament at a time. Some galaxies don't just have one supermassive black hole at their core, they have two, locked in a slow-motion dance of destruction. These dual nuclei are the aftermath of galactic collisions, where two galaxies merge, dragging their central black holes together into a shared orbit. Picture two whirlpools circling each other in a cosmic ocean, each one warping space and time with their immense gravity. Over billions of years, these black holes spiral closer, their paths tightening until they eventually collide in one of the most violent events the universe can produce. The process isn't quick. After their host galaxies merge, the black holes may take millions or even billions of years to finally meet. Friction from surrounding gas and stars slowly drains their orbital energy, causing them to inch closer over epochs. During this drawn-out waltz, their gravitational influence creates bizarre distortions in the fabric of space-time, warping the orbits of nearby stars and sending shockwaves through surrounding gas clouds. Some of these systems, like NGC 6240, are so distinct we can actually see the twin monsters glowing in X-rays as they devour matter from their accretion disks. What's truly spectacular is the finale. When these black holes finally merge, they unleash energy equivalent to millions of supernovae, shaking the universe itself with gravitational waves ripples in spacetime predicted by Einstein and first detected in 2015. These waves carry information about the black hole's masses, spins, and the violent moment of their collision, offering astronomers a new way to study these invisible giants. Future observatories like the Laser Interferometer Space Antenna will listen for these cosmic tremors, revealing mergers happening across the universe. But here's the twist: not all dual black holes merge. Some may stall just light years apart, trapped in what astronomers call the final parsec problem. Without enough nearby stars or gas to siphon away their remaining orbital energy, they could remain locked in this near embrace indefinitely, a perpetual cosmic standoff. These stalled pairs create unique environments, their gravitational tug of war flinging stars into chaotic orbits and potentially shutting down star formation across the entire galaxy. Studying these systems isn't just about black holes, it's a window into galactic evolution. Every double nucleus tells a story of past collisions, a record of how galaxies grow by consuming one another. By tracking their orbits and surrounding stellar debris, astronomers piece together timelines of ancient mergers, uncovering how today's majestic spirals and ellipticals were sculpted by violence. And somewhere out there, countless more of these pairs are hidden, waiting to be discovered, their silent dances shaping the fate of their galaxies. The universe has a way of turning destruction into creation. These dueling black holes, born from cataclysmic mergers, might one day collide and send gravitational echoes across the cosmos. Until then, they serve as reminders galaxies aren't static islands of stars, but dynamic, ever-changing entities, their histories written in the orbits of the darkest objects they harbor. And as we uncover more of these cosmic duos, we're not just studying black holes, we're reading the autobiography of the universe itself. Galaxies don't always fade quietly into the cosmic night. Sometimes they shut down with startling abruptness, like a factory halting production overnight. Astronomers call this phenomenon quenching, and it's one of the universe's most dramatic transformations. A galaxy bursting with newborn blue stars suddenly starves, its spiral arms fading to a dull red as star formation grinds to a halt. The universe is littered with these galactic retirees, their once vibrant stellar nurseries now silent. But what could possibly flip the off switch on something as vast as a galaxy? The prime suspect: supermassive black holes. When these cosmic monsters awaken, feasting on surrounding gas, they don't just consume quietly, they belch out torrents of energy in the form of searing jets and radiation. These outbursts can heat up or blast away a galaxy's remaining gas reserves, leaving nothing cool enough to collapse into new stars. It's like a gardener not just pruning a tree, but torching the soil so nothing can grow back. Galaxy NGC 1277 offers a chilling case study. Its central black hole's jets have carved vast bubbles in the surrounding gas, creating a dead zone where star formation is impossible. Once these bubbles expand far enough, the galaxy's fate is sealed. It becomes a celestial graveyard, its stars aging without replacement. But black holes aren't the only culprits. Imagine a galaxy drifting into a crowded cluster where hundreds of neighbors lurk like sharks in deep water. As it plunges through this dense environment, the surrounding hot gas acts like a cosmic pressure washer, stripping away its star-forming fuel in a process called ram pressure stripping. The galaxy's own motion becomes its undoing, leaving it gas-starved and lifeless. The Virgo cluster, just 55 million light-years away, is a gallery of these stripped galaxies, their once luminous spiral arms now frayed and faint like tattered flags in a windstorm. Then there's the strangest quencher of all, cosmic strangulation. Some galaxies aren't violently robbed of their gas, they're slowly cut off from fresh supplies, like a city under siege. Without new gas flowing in, they exhaust what they have, their star formation sputtering out over billions of years. The telltale sign: these galaxies don't just stop forming stars, they grow redder as their most massive, short-lived blue stars die off, leaving behind cooler, longer-lived red stars. It's a slower, more agonizing end than the violence of black holes or ram pressure, but no less final. What makes quenched galaxies so fascinating is what they leave behind: cosmic time capsules. Their stellar populations freeze in time, preserving a snapshot of the moment star formation ceased. By studying their chemical compositions and ages, astronomers can reconstruct their histories like forensic scientists piecing together a cold case. Some reveal layers of stellar generations, hinting at multiple quenching attempts before the final shutdown. Others, like the red spirals found in galaxy clusters, defy expectations, their delicate spiral arms intact but eerily devoid of young stars, as if frozen mid-transformation. The universe, it seems, has many ways to silence a galaxy. Whether by black hole fury, environmental robbery, or slow starvation, quenching reshapes the cosmic landscape, turning vibrant star factories into relics of a more active past. And as we uncover more of these galactic ghosts, we're left with a humbling thought. Even the mightiest structures in the universe aren't immune to change. The same forces that give birth to galaxies can also bring about their twilight, leaving behind not just corpses, but clues to the cycles that govern all things cosmic. The Milky Way isn't traveling through space alone. It's surrounded by a retinue of tiny satellite galaxies, cosmic attendants orbiting our own like moths around a flame. But here's the catch: these satellites aren't scattered randomly. Instead, they're bizarrely aligned along a thin, flat plane, almost as if someone strung them on an invisible disk around our galaxy. This isn't just a curiosity, it's a full-blown cosmic mystery, one that challenges everything we thought we knew about how galaxies form and evolve. For decades, astronomers assumed satellite galaxies would be distributed more or less evenly around their host, like bees buzzing around a hive. That's what computer simulations predicted, based on our understanding of dark matter's gravitational pull. But reality had other plans. When researchers mapped the positions of the Milky Way's satellites, they found nearly half of them, including the large and small Magellanic Clouds huddled in a narrow plane, like a celestial conga line. Even stranger, many of them orbit in the same direction, moving in sync like dancers following choreography. This isn't just unlikely, it's statistically jarring, a cosmic coincidence that defies standard models of galaxy formation. So how did this happen? One tantalizing theory suggests these satellites weren't always separate galaxies. Instead, they might be the mangled remains of a single, larger dwarf galaxy that ventured too close to the Milky Way billions of years ago. Picture a galactic wrecking ball. Our galaxy's immense gravity could have torn this interloper apart, stretching its stars and dark matter into a long stream that eventually fragmented into the satellites we see today. The alignment would then be a fossil of that ancient collision, a ghostly imprint of a violent past. Evidence for this comes from the satellite's similar chemical compositions, hinting they share a common origin. But there's another, even more mind-bending possibility. Dark matter might be shaping their orbits in ways we don't yet understand. If the Milky Way's dark matter halo isn't a smooth, spherical cloud but a flattened disk or a series of dense filaments, it could funnel satellites into these peculiar paths. Some theories even propose that dark matter interacts with itself through unknown forces, creating structures that guide satellite galaxies into alignment. It's a reminder that for all we've learned about dark matter, its true nature remains one of astronomy's greatest enigmas. The implications ripple far beyond our galactic backyard. Other galaxies, like Andromeda, also show signs of similarly aligned satellites, suggesting this isn't a fluke. It might be a universal feature we've overlooked. If so, our models of galaxy formation need serious revision. Are we missing a key piece of physics? Could dark matter be stranger than we imagined? Or is there some ancient, chaotic event, a collision, a near miss, a gravitational tug-of-war that left its mark on these satellites? Every new observation deepens the mystery. Recent studies of ultra-faint dwarf galaxies, so dim they were only discovered in the past decade, show some follow the same puzzling plane while others don't. This mix of alignment and randomness only adds to the confusion, as if the universe is teasing us with half-answered questions. Upcoming telescopes like the Vera C. Rubin Observatory promised to uncover even more of these faint satellites, potentially revealing patterns we can't yet see. What's certain is this: the Milky Way's satellites aren't just passive bystanders. They're clues to our galaxy's violent history, to the nature of dark matter, and to the forces that sculpt the cosmos on the grandest scales. Their odd alignment is a cosmic puzzle waiting to be solved, one that might rewrite the story of how galaxies and the universe itself came to be. And until we crack it, these tiny galaxies will keep orbiting in their strange, synchronized dance, whispering secrets we're only beginning to hear. Galaxies don't just fade away when their star-forming gas runs low. They can stage cosmic comebacks, reigniting like phoenixes from the ashes of their own demise. This process, known as galactic recycling, turns what seems like an ending into a new beginning. Picture a forest fire that doesn't just destroy but enriches the soil, allowing fresh growth to emerge. In galaxies, the soil is the gas expelled by dying stars, supernova, and stellar winds, material that eventually cools, condenses, and falls back into the galactic disk, ready to fuel another round of star birth. It's the universe's ultimate sustainability program, ensuring galaxies don't just burn out but can cycle through periods of dormancy and rebirth. The Phoenix cluster is the poster child for this phenomenon. At its heart lies a galaxy that should have been dead, its gas reserves scorched away by the blistering heat of the surrounding cluster, yet somehow it defied expectations. Cold gas began raining back into the galaxy's core, sparking a stellar renaissance so intense it now produces around 700 new stars per year, a rate dwarfing our Milky Way's modest output. This isn't just a fluke, it's a testament to the universe's ability to recycle on a staggering scale. The secret lies in the delicate balance between heating and cooling. While the cluster's superheated gas should prevent star formation, pockets of cooler gas manage to slip through like raindrops surviving a desert wind. But how does expelled gas find its way back? The answer lies in gravity's patient pull. When massive stars die in supernova, they blast their outer layers into space at incredible speeds, but over millions of years that material slows, pulled back by the galaxy's gravity. Similarly, stellar winds from aging stars carry gas outward, only for it to eventually cool and tumble back inward. Even the supermassive black hole at a galaxy's center, often a force of destruction, can indirectly aid recycling. Its jets and outbursts stir up surrounding gas, creating turbulence that helps some of it cool and condense, like a cosmic blender mixing hot and cold ingredients. This cyclical process explains why some galaxies, long thought to be red and dead, suddenly flare back to life. Take Messier 87, the massive elliptical galaxy famous for hosting the first photographed black hole. Observations reveal faint traces of recent star formation, suggesting it's not entirely dormant gas from ancient stellar deaths, maybe quietly fueling new births in its outskirts. Even our Milky Way recycles. The high-velocity clouds of gas streaking through our galactic halo are likely the returning remnants of past stellar explosions, destined to replenish the star-forming reserves of future epochs. What's breathtaking is the timescale of this recycling. A single loop from gas expulsion to cooling to recollapse can take hundreds of millions of years. That means the material forming stars today might have been part of a supernova blast or a red giant sigh when dinosaurs still walked the Earth. And the elements crucial for life, carbon, oxygen, iron, are continually redistributed through this process, ensuring each generation of stars has the building blocks for planets and potentially life. The implications are profound. Galactic recycling means no galaxy is ever truly dead, just waiting for the right conditions to reignite. It also reshapes our understanding of cosmic evolution. Instead of a linear march toward stagnation, galaxies may pulse with activity in cycles, their fates tied to the ebb and flow of their own recycled materials. As telescopes peer deeper into clusters and galactic halos, they're uncovering more of these rebirths, hinting that the universe's story isn't one of inevitable decline, but of endless renewal. And in that realization lies a humbling truth. Even on the grandest scales, nothing is ever truly wasted, just transformed, reused, and reborn. There's a cosmic deadline looming over astronomy, one that's ticking away silently as the universe expands. The most distant galaxies, those flickering candles from the dawn of time, are slowly but surely fading from our view, their light stretched and diluted by the relentless expansion of space. Imagine holding a photograph underwater, watching as the ink bleeds and the image dissolves into nothingness. That's what's happening to the light from these ancient galaxies, redshifted so severely that their visible light becomes infrared, then radio waves, and eventually undetectable noise lost in the void. The James Webb Space Telescope, with its infrared eyes, is racing against this clock, capturing snapshots of galaxies like GNZ 11 before they slip forever beyond our observational reach. The culprit here isn't just distance, it's the accelerating expansion of the universe driven by dark energy. Every second, the space between galaxies grows, stretching the wavelengths of their light like taffy. For the most distant objects, this stretching is so extreme that their light, already billions of years old by the time it reaches us, is pushed beyond the limits of our detection. It's as if the universe is rewinding a tape, but the farther back we go, the more the audio distorts until only silence remains. Future astronomers, peering through telescopes 100 or 1,000 years from now, will see far fewer of these ancient galaxies than we do today. Their cosmic horizon will be narrower, their window into the early universe dimmer. What's at stake isn't just a handful of distant smudges, it's the story of how galaxies formed, how the first stars ignited, and how the cosmos evolved from darkness to light. These fading galaxies are our only direct witnesses to the universe's infancy. Take Max 1149 JD, a galaxy so distant its light comes from a time when the universe was just 500 million years old. It's a Rosetta Stone for understanding how tiny proto-galaxies merged into the giants we see today. But as space stretches, galaxies like this will cross a threshold where their light can no longer reach us, no matter how advanced our technology becomes. The universe, in effect, is erasing its own history. This isn't a distant future scenario, it's already happening. The light from galaxies at the very edge of our observable universe is redshifted to such extremes that only the most sensitive instruments can detect them. Over billions of years, even closer galaxies will succumb to this cosmic vanishing act. The local group, our Milky Way, Andromeda, and their satellites will one day be all that's visible, their light trapped in a gravitational bubble while the rest of the universe recedes into darkness. Civilizations born in that far future will have no way of knowing the universe was once teeming with galaxies, no clue that expansion was ever slower, no evidence of the cosmic web that once connected everything. That's why missions like Webb and next-generation telescopes are so critical. They're not just exploring the distant universe, they're salvaging cosmic heritage before it's lost forever. Every galaxy they document, every spectrum they capture, is a time capsule for future generations. The race to study these objects isn't just about science, it's about preserving a vanishing record of existence itself. And in that urgency lies a profound lesson. The universe isn't static, and our ability to understand it has an expiration date. The window is closing, and we're among the last observers positioned perfectly in time to glimpse the full grandeur of cosmic dawn before it fades to black. Galaxies aren't just vast islands of stars and gas, they're threaded with invisible magnetic fields stretching across millions of light years, like cosmic spiderwebs woven through the void. These force fields are unimaginably faint, billions of times weaker than a fridge magnet, yet they shape the very fabric of galactic life. They guide the paths of high-energy cosmic rays, sculpt the flow of interstellar gas, and even influence where stars are born. But how does something so intangible arise on such a colossal scale? The answer lies in the universe's most elusive physics, where magnetism becomes a ghostly architect of galactic destiny. The Milky Way's own magnetic field is a perfect example, a sprawling, chaotic network that twists through its spiral arms. Astronomers have mapped its faint imprint by studying the polarization of starlight, which shifts slightly as it passes through magnetized dust. What they've found is astonishing. Our galaxy's field isn't a neat, orderly pattern but a turbulent tangle, with loops and filaments stretching tens of thousands of light years. It's like a stormy ocean where magnetic waves crash and swirl, channeling particles and energy across unimaginable distances. But where do these fields come from? One theory traces their origins to the infant universe, when quantum fluctuations in the Big Bang's aftermath might have seeded weak magnetic fields. Over billions of years, as galaxies formed and rotated, these primordial fields could have been amplified and stretched, like taffy pulled thin by cosmic motion. Another possibility involves galactic dynamos, a process where swirling plasma in a galaxy's disk generates magnetic fields through sheer kinetic energy, similar to how Earth's molten core creates our planet's magnetism. Picture a gigantic, slow-motion generator, powered by the rotation of stars and gas, spinning up invisible forces that ripple through the cosmos. The most mind-bending aspect of these fields is their sheer scale. In galaxy clusters, magnetic fields don't just stop at the edges of individual galaxies, they extend into the void between them, linking galaxies together like beads on an invisible string. The Coma cluster, for instance, hosts a magnetic field so vast it blankets the entire cluster, influencing the motion of charged particles across millions of light years. These intergalactic fields are thought to arise from the violent turbulence of galaxy collisions, where shockwaves and plasma flows twist and amplify magnetism into a sprawling cosmic net. What's truly humbling is realizing how much we still don't know. Magnetic fields are invisible to conventional telescopes, requiring ingenious techniques to detect their subtle influence. Even then, their behavior defies simple explanation. Some galaxies, like Messier 82, exhibit magnetic fields so strong they launch jets of charged particles far into intergalactic space. Others, like the Andromeda galaxy, show fields that align bizarrely with their spiral arms, suggesting forces we haven't yet unraveled. These fields aren't just cosmic decoration, they're active players in galactic evolution. By channeling cosmic rays and stabilizing gas clouds, they help determine where and how stars form. They might even shield galaxies from external radiation, acting as invisible force fields against the harsh interstellar environment. And as we peer deeper into the universe with radio telescopes and polarization-sensitive instruments, we're uncovering more of these hidden magnetic landscapes, each one a clue to the unseen forces shaping the cosmos. The next time you gaze at the Milky Way's shimmering band, remember, you're not just seeing stars, you're witnessing the glow of a galaxy wrapped in an invisible embrace, its destiny quietly guided by magnetism's silent hand. And somewhere out there, another galaxy's magnetic field stretches into the darkness, weaving its own unseen story into the fabric of the universe. Some galaxies are cosmic phantoms so faint and wispy they nearly vanish against the backdrop of space. These are ultra-diffuse galaxies, mysterious structures that defy the typical image of a galaxy as a dense, glittering metropolis of stars. Picture a sprawling city with only a handful of streetlights, its streets so dark and empty you could walk for miles without seeing another soul. That's what it would be like inside one of these ghostly realms, where stars are so scarce you could travel from one end to the other and count them on your hands. Their existence is baffling. Despite spanning sizes comparable to the Milky Way, ultra-diffuse galaxies contain just 1% of its stars, making them nearly invisible to traditional telescopes. Some, like Dragonfly 44 in the Coma cluster, are so dim they were only discovered when astronomers meticulously subtracted the light from all other visible objects, revealing a faint, glowing haze that had been hiding in plain sight. What's even stranger is their weight or lack of it. These galaxies are far lighter than their size suggests, as if the universe forgot to pack them with enough matter. So how did they form? One theory suggests these are cosmic underachievers, galaxies that never got the chance to shine. Early in the universe, they might have formed in regions where gas was too scarce or too hot to collapse into stars, leaving them frozen in a half-finished state. Another possibility is that they're the remnants of galactic violence. Imagine a spiral galaxy like our own being pulled apart by tidal forces, its stars scattered like dust in the wind. Over time, the brightest stars fade or are stolen, leaving behind only the dimmest, oldest stars drifting in a loose, ghostly halo, but the plot thickens. Some ultra-diffuse galaxies, like NGC 1052DF4, seem to lack dark matter entirely, the very substance thought to be essential for galaxy formation. This discovery sent shockwaves through astronomy, forcing scientists to reconsider how galaxies take shape. Could these ethereal structures have formed without dark matter's gravitational scaffolding? Or was it somehow stripped away, leaving behind a skeletal remnant of what once was? The hunt for these cosmic ghosts is rewriting galactic rulebooks. With every new detection, we're forced to confront how little we truly understand about the diversity of galaxies. They might be faint, but their implications are anything but challenging our assumptions about dark matter, star formation, and the very nature of cosmic evolution. And as telescopes grow more sensitive, who knows how many more of these phantoms are lurking in the darkness, waiting to be found. Some of the universe's most violent explosions leave behind more than just debris. They create ripples of light that reverberate through space for centuries, like cosmic applause long after the performer has left the stage. These ghostly afterimages, known as light echoes, occur when the flash of a supernova or other cataclysmic event bounces off clouds of interstellar dust, creating delayed reflections that can reach Earth decades, or even millennia after the original explosion faded from view. It's as if the universe itself is playing a game of celestial telephone, whispering secrets from the past across generations of stargazers. Take the case of Eta Carinii, a volatile star system that erupted in the 1840s, briefly becoming the second brightest object in the night sky. While the original outburst faded within years, Astronomers in the 21st century are still observing its light echoes ghostly rings of illumination expanding outward at the speed of light, reflecting off dust clouds hundreds of light years away. Each echo is a time capsule, preserving the exact spectrum and intensity of the original eruption, allowing scientists to dissect an event their ancestors witnessed nearly 2 centuries ago with modern instruments. The result, we now know Eta Carinae's explosion wasn't a traditional supernova, but a bizarre, half-stellar eruption that spat out enough material to build 10 solar systems, all while the star somehow survived. But light echoes aren't just about revisiting old explosions, they're rewriting history. In 2008, astronomers studying the light echo of a 16th century supernova witnessed by Tycho Brahe discovered something shocking. The explosion wasn't the standard Type Ia supernova everyone assumed, but something far stranger. By analyzing the reflected light's chemical fingerprints, they realized this cosmic fireball defied classification, challenging decades of supernova theory. It's like uncovering a lost manuscript that contradicts everything we thought we knew about a pivotal historical event. The most haunting echoes come from long-dead stars whose original outbursts predate human civilization. Around the constellation Cassiopeia, light from a supernova that exploded 11,000 years ago is still ricocheting off dust clouds, creating ethereal, ever-expanding shells visible only to the most sensitive telescopes. These delayed messengers carry information from a time when Earth's glaciers were retreating and humanity was taking its first steps toward agriculture. By studying them, we're not just observing the past, we're touching it, measuring the exact temperature and composition of stellar explosions that occurred before the pyramids were built. What makes light echoes truly revolutionary is their ability to turn the galaxy into a hall of mirrors, where single events can be studied from multiple angles over vast stretches of time. A supernova's light might reach Earth directly first, then centuries later, we catch its reflection from a dust cloud located slightly off-axis, revealing how the explosion looked from a different perspective. It's the closest thing astronomy has to a time machine, offering 3D snapshots of cataclysms that shape the chemical evolution of galaxies. And as our telescopes grow more powerful, these faint whispers from the past will only grow louder, revealing hidden chapters in the epic story of stellar life and death. The next time you gaze at the Milky Way's dusty lanes, remember, those dark clouds aren't just voids. They're cosmic recording devices, silently capturing the flashes of dying stars, waiting for the right moment to play them back. In a universe where light takes time to travel, even the past isn't truly gone, it's just waiting to echo. We think of galaxies as enormous, but in the grand scheme of the cosmos, they're mere specks, tiny building blocks in structures so vast they defy human comprehension. Meet the superclusters, the universe's true titans. These sprawling metropolises of galaxies stretch across hundreds of millions of light years, their gravitational pull weaving thousands of galaxy clusters into a single, interconnected web. If a single galaxy is a city, a supercluster is an entire continent, with galaxies as its towns, star clusters as neighborhoods, and dark matter as the invisible glue holding it all together. The Milky Way doesn't drift through space alone. It's part of the Laniakea supercluster, a name from Hawaiian meaning immeasurable heaven. This cosmic behemoth contains over 100,000 galaxies, all moving collectively toward a mysterious gravitational focal point called the Great Attractor, hidden behind the dust of our own galaxy's central plane. Picture a river system with smaller streams feeding into larger ones. Galaxy groups flow into clusters, clusters into superclusters, all tracing the contours of gravity's grand design. Laniakea spans 500 million light-years, a size so staggering that if you traveled at light speed, you'd need 500 million years just to cross it. But Laniakea isn't the only supercluster, it's just our local neighborhood. Beyond it lies the even larger Shapley supercluster, a gravitational heavyweight pulling entire galaxy clusters into its orbit. Then there's the Saraswati supercluster, discovered in 2017, a structure so ancient it formed when the universe was barely half its current age. These giants aren't just random assemblies, they trace the underlying skeleton of the cosmos, revealing where dark matter's gravitational tendrils have drawn galaxies together over billions of years. What's truly mind-bending is how these superclusters fit into the cosmic web. They aren't isolated islands but interconnected nodes in a filamentary network spanning the observable universe. Between them lie vast, nearly empty voids, regions so devoid of matter they stretch hundreds of millions of light-years across, creating a cosmic foam-like structure. The Pisces-Cetus supercluster complex, for instance, is a filament of superclusters winding through space like a serpent, linking countless galaxies in a delicate gravitational dance. Yet even these titans are temporary. Over trillions of years, as dark energy accelerates the universe's expansion, superclusters will be torn apart, their galaxies stranded in isolation. For now, though, they stand as the ultimate testament to gravity's power, not just to pull objects together, but to sculpt the universe itself into a tapestry of unimaginable scale. And as we map more of these structures, we're not just charting space, we're reading the story of how gravity wrote the cosmos into existence. Hidden beneath the darkness between galaxies lies a secret highway, a sprawling network of ghostly threads that may hold the key to one of astronomy's greatest mysteries. These cosmic filaments, wispy tendrils of hydrogen gas stretching millions of light years, weave galaxies together like beads on an invisible string. For decades, supercomputer simulations predicted their existence, showing how the universe's large-scale structure should resemble a web, with galaxies clustered at the intersections of these gaseous threads. But catching a glimpse of them proved nearly impossible until astronomers turned to some of the most violent objects in the cosmos for help. The breakthrough came from studying quasars, the blazing cores of distant galaxies powered by supermassive black holes. As their light travels across the universe, it passes through these filaments, leaving faint absorption lines in their spectra, like fingerprints in starlight. Slowly, painstakingly, researchers pieced together a map of this hidden network, revealing hydrogen gas so diffuse it's barely denser than a few atoms per cubic meter. Yet despite its ghostly thinness, this web might contain up to half of all the normal matter in the universe, the very baryonic particles that make up stars, planets, and us. What's astonishing is how these filaments act as cosmic fuel lines. Gravity slowly funnels gas along these threads toward galaxies, providing the raw material for new stars. Picture a tree's root system drawing water from the soil, only here, the roots are invisible tendrils of hydrogen, and the water is the lifeblood of galactic evolution. Without this constant inflow, many galaxies would have exhausted their star-forming gas billions of years ago. The Milky Way itself might be fed by these filaments, with gas trickling in from the local sheet, a flattened region of the cosmic web surrounding our galactic neighborhood. But the real revolution is how these filaments could solve the missing baryon problem. For years, astronomers faced a paradox. Their inventories of ordinary matter, protons, neutrons, and electrons, fell short of theoretical predictions by about 30%. The answer, the missing matter, wasn't missing at all. It was hiding in these faint, diffuse filaments, too dim for most telescopes to detect. Only by combining observations from X-ray satellites, radio telescopes, and quasar studies could researchers finally account for nearly all the universe's expected baryons, closing one of cosmology's most persistent gaps. The latest discoveries push the boundaries even further. In 2021, the Keck Cosmic Web Imager captured the first direct images of these filaments glowing faintly around a distant galaxy cluster, their structure eerily matching supercomputer predictions. Meanwhile, the Atacama Large Millimeter Array has spotted cold gas streams flowing along filaments into hungry galaxies, like rivers feeding a growing city. Each observation peels back another layer, revealing how this cosmic plumbing shapes everything from star formation to the distribution of galaxies across billions of light years. Yet for all we've learned, the cosmic web remains full of mysteries. How do magnetic fields thread through these filaments? What role do they play in accelerating cosmic rays? And could dark matter's gravity be shaping their structure in ways we haven't yet detected? As telescopes grow more sensitive, we're not just mapping the universe's visible skeleton, we're uncovering the invisible currents that have guided its evolution from the Big Bang to the present day. What was once theoretical speculation is now a vibrant field of discovery, proving that even the emptiest corners of space are brimming with hidden connections. From the mind-bending scale of galactic collisions to the invisible grip of dark matter, these revelations paint a universe far stranger and more wondrous than we often dare to imagine. Every discovery peels back another layer of cosmic mystery, like turning the pages of a book written in the language of gravity, light, and time. Think about it, galaxies so vast they defy comprehension, black holes that warp the fabric of reality, and invisible forces shaping everything we see. Yet for all we've uncovered, these are just the first whispers of a story spanning billions of years. What's exhilarating is how much remains hidden. For every question answered, like why some galaxies lack dark matter or how the cosmic web connects the universe, dozens more emerge, each one more tantalizing than the last. The James Webb Space Telescope has already upended our understanding of the early universe, revealing galaxies that shouldn't exist as early as they do. Meanwhile, upcoming observatories like the Vera C, Rubin Observatory and the Square Kilometer Array promise to expose even deeper secrets, from the nature of dark energy to the faintest, most elusive galaxies drifting in the void. This isn't just about cataloging celestial objects, it's about rewriting the story of existence itself. Every time we point a telescope skyward, we're not just observing, we're time-traveling, piecing together a cosmic puzzle where each fragment reveals another clue about how galaxies are born, evolve, and sometimes fade into silence. And the most humbling part, we're not passive observers. The very atoms in our bodies were forged in the hearts of stars, scattered across space by supernovae, and woven into planets by the same forces that shaped galaxies. We're not just studying the universe, we're stardust trying to understand itself. So what's next? Perhaps we'll find galaxies even older than GNZ 11, pushing the timeline of cosmic dawn further back. Maybe we'll crack the code of dark matter or witness the birth of a supermassive black hole. Or perhaps the biggest discoveries will be the ones we can't yet fathom. The cosmic curveballs that force us to rethink everything we thought we knew. That's the thrill of astronomy. The universe always has another surprise up its sleeve. As you look up at the night sky tonight, remember, you're not just seeing stars. You're gazing at a dynamic, ever-changing cosmos where galaxies collide, black holes dance, and invisible forces sculpt the fabric of reality. And this journey is far from over. If these 25 facts left you awestruck, just wait. The next chapter of cosmic discovery is already being written. Share your favorite revelations in the comments, And don't forget to subscribe for more deep dives into the universe's grandest enigmas. The cosmos is vast, mysterious, and endlessly captivating, and we're only just beginning to explore